So thanks everybody for joining. Obviously, packed house here. I do want to look at, or I will be looking at trying to make this more regular and get a conference room reserved for the entire spring semester. So we'll be looking at that. And then we'll be looking at starting this back up in the spring semester as far as sometime in January. So look for announcements though, not until the next, the new year on presentations or call for presentations. I had a few that came up that I think we'll be looking forward to in the spring semester. But otherwise, thanks for everybody for joining us here on this last one of the fall semester on this Reading Days Eve. I know everybody's likely very busy either with classes or putting classes together or something along those lines. So thanks for joining us anyways here. And we're very glad and I'm very thankful that Dr. Elena Lin is going to talk to us about her work in maybe different areas of spectroscopy. So with that, I'll take it, turn it over to you.
Okay, well, thank you, everybody. So I always debate with myself what presentation should I give, and I go from either being extremely technical to being very high level. So for students, I decided to get a little bit more technical today. And so how much time do we have, Kevin? About
we have the entire hour for an hour.
So this is a pretty kind of intense presentation, but I will try to kind of put it in perspective so it's easier to appreciate it. And for those of you who took radiative transfer, remote sensing class, hopefully at least something will be familiar. All right, so I'm going to start sharing my screen. So my sort of path to the into the remote sensing started with really the NASA path in a sense. Through my PhD, I built an instrument to validate ozone monitoring instrument products, which are trace gases, mainly nitrogen dioxide, formaldehyde, sulfur dioxide. So why would ever NASA be interested in doing any Earth's atmosphere trace gas measurements? In theory, it actually started because of ozone. So in 1985, we discovered that our production of freons and wide usage of freons resulted in propagation of those chlorinated chlorofluorocarbons to the stratosphere, and at the stratospheric level, they were contributing to the destruction of ozone. Obviously, at that point, that was like one of the biggest tasks that was given through the Montreal Protocol, is not only to stop production of freons, but also to absorb the ozone in the atmosphere. So this is actually a congressional mandate, both to NOAA and NASA. They all, by the books, have to measure ozone around the world from the satellite platforms. So what is ozone? So we all know that there is ozone in the stratosphere that protects us from UV radiation. It's extremely valuable. If we remove that layer, nothing will survive on this planet that is of biological nature. However, we have ozone also through the troposphere. So when I talk about stratosphere, I'm talking about above 12 kilometers, and troposphere, it's between surface and up. So ozone is kind of one of those, the good and the bad guys. If it's in the right place, it's a good. If it's in the wrong place, it's a strong oxidant. And it's actually responsible for agricultural damage, like in billions of dollars annually, if it's at the surface level. And you might be saying, like, why would it be at the surface level? Well, the reason for that is our pollution. So as the industry emits various chemicals, mainly nitrogen oxides that are produced during the combustion of the fossil fuels or any kind of biological combustion, and organic compounds that might be actually in the atmosphere due to the tree emissions or also in the industry produced. So if you mix everything together and add a little bit of radiation from above, you start hitting sort of the atmospheric chemistry, and that would result in ozone production, and that results in, you know, asthma, you know, trips to you know, like emergency rooms for people who are sensitive, to damage to the foliage of plants, like especially like peanuts, you know, like other plants are quite sensitive to it. So then you go a little bit higher up, and there is ozone in the free troposphere, mid-troposphere part. And at this level, it's actually good because it helps us destroy the pollution that ends up being emitted from the surface. And then if you go a little bit higher, we have, again, ozone that is a bad guy in that particular case. And the reason why it's bad guy, because it's now a greenhouse gas. So obviously, we don't want anything here, we don't want anything here, and we want these guys here. So the whole idea behind how do you actually measure, and how do you, is it enough to measure just the ozone, or do we need to measure something else? I mentioned earlier that we have nitrogen oxides that are contributing to the bad ozone at the surface. We also have various organic compounds, and most of them, as a result of this photochemistry, will end up producing formaldehyde. You know, formaldehyde is something like a preservative or whatever that is used in museums, but formaldehyde is actually being also formed in the atmosphere as a result of all this chemistry. So the bottom line, if you really want to understand what ozone is doing, you also need to understand what nitrogen oxides are doing, and what formaldehyde is doing, what sulfur dioxide is doing, and so forth. And this is pretty much the motivation, behind it. So obviously, you know, what they are doing is extremely complex, considering the complexity of physical, biological processes, various transport processes, photochemistry, chemistry, and you name it. So this is just kind of a diagram for that. So the idea is really, how do you actually monitor this? Ideally, we all want to model it. Ideally, we want to just tweak a few knobs, you know, put the right inputs, and the model, chemical transport models, will just produce you everything. Obviously, life is not that easy. So we need to monitor, and the most efficient way, obviously, to monitor this will be from space. So this is, you know, just a kind of demonstration. So to have this production of ozone at the surface and aerosols, you need this volatile organic compounds, NOx, radiation, UV radiation, and you're done. So this is smog. As you remember, you know, LA is famous, or has been famous for smog. And China, you know, like taking its roles. Now it's India, Bangladesh, you know, like, you know, all kinds of countries that are catching up with these problems. Obviously, models are not doing super well because they have to have all this information and all the chemistry properly, you know, like modeled, all the inputs, all the inventories of the emissions, and that's quite significant, especially as our technology and lifestyle and the regulations change. So the next best solution will be to use satellites. So the satellite monitoring is great because you can have a full coverage of Earth if you're in sun-synchronous orbits. Usually it's once per day. You can kind of fly over the same location at about the same time and have this full coverage. Now we are seeing next generation of air quality instruments that actually are located in geostationary orbit. So the first one was GEMS, that is hovering over Asia. The next one will be Tempo, actually an American instrument that will be hovering over North America, and then there will be European Sentinel-4 that will actually cover the European section. So in those cases, we are going to have hourly average of the pollution distribution. So the problem with the satellite measurements is that how do you know that they are right? Depending where the instrument is, you might be, just 500, 600 kilometers above, or you can be 35,000 if you're in, geostationary orbit. So what does this mean? That means that we need to understand what the measurements are doing, and we need to be able to validate. So what's the problems? Well, the problems, as you see, a lot of these instruments are backscatter instruments. So the solar radiation propagates through the atmosphere, scatters of whatever is in the atmosphere and the surface, and gets back detected, backscattered and detected by the instrument. So obviously the reflectivity, the surface reflectivity of whatever it's looking, and you can think about footprint of each pixel, the potential heterogeneity, think about clouds that might be blocking some of the information that is coming back. Obviously, think about any kind of heterogeneous breaks or land-water interfaces, and all those cases, satellites are going to have some uncertainties. So how do we validate them? So one of the techniques that have been developed, and I'm not expecting you to read all this, it's called differential optical absorption spectroscopy. By the way, this is the technique, this is the main technique that is used by the satellite instruments themselves. And I'll go into detail, but the best way to really validate what the satellite is seeing, obviously, is to have the measurements here at the ground doing the same thing. So the uncertainties are smaller, you have much more control, you can validate or actually calibrate the instruments if you need to. So this is what is done. So like for all these measurements, you usually have ground-based validation networks now that are operating on this principle of differential optical absorption. Multi-axis technique is relatively new. It's about, from about early 2000s, this technique started appearing, and I'll give you the details about it in a second. But the idea is that you can, with various types of the technique, you can actually provide the information that is comparable and better quality than what measuring the same species and the same property, but much better quality than the satellite will see. So the basic idea is very simple. You have a light source, in this case, it's sun. You have the atmosphere, you have an instrument that is a spectrograph, moderate resolution spectrograph. We're talking about 0.5 to 1 nanometers per full width at half max. And this is extremely old picture. And then obviously, like you measure detectors, it's typically CCDs. This is a spectrometer with diffraction gratings or holographic gratings, depending on, the technology. And you are recording the entire spectrum. So from the electromagnetic fields, you're probably remembering what's going to happen in this atmosphere. As a result of it, propagation, obviously we have molecules, we have particles, we have water droplets like clouds and things like that. So how does it look really? How this technique works? So the idea is very simple. So you have a spectrum with moderate resolution, and you are trying to extract the information that those photons are carrying with them. So think about every time the photon is interacting with molecules, it's going to be either be absorbed or scattered. It's going to interact with particles, the same, clouds. And as those photons propagate through that atmosphere, it's actually carrying that signature. So it's all there. It's just the question, can we extract that information? So how does this particular technique extract it? So it's called differential optical absorption spectroscopy. So it's based on the Beer's law. And the Beer's law is I. This is attenuated intensity is equal original intensity of the source times exponent of sigma LC. So sigma, it's absorption cross-section of whatever species you have. C is concentration, and L is a path the photons traveled through that medium. So obviously reality is a little bit more complex there because we have scattering in addition to absorption. It's kind of like nice because Rayleigh scattering and mis-scattering or Ersal scattering does not really have structure to it. So it means that it's fairly broad. On the other hand, the trace gases are very structured, so there is high frequency dependency of the absorption cross-section itself. So as a result, this technique is doing this. It's saying, okay, this is all wonderful. We're going to split our Rayleigh and mis-scattering and use polynomial order to actually fit it. And we're going to take whatever else is left or differential structure, and we're going to do a nonlinear least squares fit of various structures scaled by a specific value. So in a sense, you're kind of looking at this. So this is a polynomial that is going to be removed, and whatever is left is going to be fitted to this cross-section. So how do those cross-sections look like, and what do we usually have? So here's an example. Remember, there is this differential part. You do not have to kind of take the differential to make that equation, but just for the sake of like exercise, I'm going to show it. So this is a glyaxal, water vapor, oxygen collision complex, nitrogen dioxide, honor, bromine monoxide, formaldehyde, sulfur dioxide, and ozone. And so this is the cross sections. And you can see how unique they really are. Obviously, because they have different molecular structure, they will absorb differently. And the beauty of this particular compounds is that they're in this atmospheric window. What does it mean? That the atmosphere is not going to absorb other than for this species. There will not be much attenuation by other gases like greenhouse gases, because they absorb mostly in infrared. So here's a differential structure. So look at this ozone, it has pretty high absorption rates near 300 nanometers, but the differential structure kind of looks like this. So you can see that if I am fitting in this particular window, it's a hyperspectral fitting. It means that I'm fitting multiple wavelengths at the same time. So imagine I'm taking like from 300 nanometers to 360 nanometers. And in theory, I should be able to retrieve all those gases because they have different structure. In reality, life is a little bit more complex because the instruments actually having different noise levels, and there's some crosstalk, but this is not for this discussion. So how does the sun spectrum itself looks like? So this is the kind of simple, this is outside the atmosphere, this is inside. Obviously we have absorption by ozone and this smaller absorption, but you can see in the wavelength region that we are looking here, most of this scattering and absorption that we are totally can handle. The things that we do need to pay attention is the Fraunhofer lines, the lines that are actually absorption lines from the solar photosphere itself. And because we're going to feed the structures, it's extremely important to make sure that we can remove this solar structure from our measurements. Okay, so when we talk about the observations, it's where we are pointing the instrument and where the photons are coming from, and depends on what kind of information they're going to carry. So if, for example, we're looking straight at the sun, in a sense, we know fairly well how the photon is going to travel. It's a pure geometry in a sense. I'm not keeping up with time. I probably should have brought a clock somewhere here, but Kevin, I'm going to just wave at me at some point so I don't go over time.
Yeah, no, you're good.
So if you're looking straight at the sun, the photons are just going to travel right towards you. So you know where the sun is, you know where you are. You can pretty much calculate the path. There's no real sensitivity to the profile where exactly your pollution was, unless you're at very, very high solar-zenith angles. The other observation geometry, and note that you can combine everything to really squeeze out all the information you can. So the other is looking straight up. This is the measurement that, in a sense, started this DOAS technique. Just looking up and letting the photons travel through the stratosphere as the sun is setting down and during the twilight time. So you can think about twilight when the sun is below the horizon, so it's here. So the photons really are traveling a very long path through the stratosphere and then being detected. So you can really get the stratospheric layer. So remember, everything started with ozone hole motivation. So nitrogen dioxide, ozone in the stratosphere were of big interest. So this is where historically it began in mid-1970s. And the max DOAS or multi-axis technique is now, okay, like we're more interested, or we're quite interested in tropospheric information profiles. So now we're looking actually really low down and scanning the horizon at multiple angles and trying to catch those photons that are undergoing multiple scattering within the lowest part of the atmosphere. So this one, again, is more sensitive to the stratospheric values. This one, if you look at this one and the max DOAS, do you see in a sense what's happening above in the stratosphere? It's fairly similar between them at solar-zenith angles, roughly up to 75 degrees. So if I have this measurement and I use this as a reference, remember there is in Beer's law I over I naught. I naught ideally is extraterrestrial. Obviously, we don't have the luxury to jump outside the atmosphere to catch that spectrum. So you need to have a reference. So here it will be this zenith looking up will be my reference for this measurements. And what it does, it pretty much cancels out the information from above, and the only thing I'm left with is information from below. So in a sense, if you combine all this technique, you can get total information, zenith, stratospheric information, and then you can get the low tropospheric information. So obviously life is not that simple. And we have aerosols. And those aerosols obviously have properties, they have size, they have different structure, they scatter differently, there's different size distributions, there are different number of them. We have clouds. Obviously all this results in multi-scattering events. So what you're actually measuring is this path, the photon, the information. So this what we call differential, the differential slam column density, or the amount of the absorption by X number of molecules along this convoluted path. Like we don't really know that path ahead of time, so we just measure, and then our goal is really to retrieve that information so we can go from this ambiguous column information to something vertical that is much more meaningful. So where are our problems? Clouds. We need to know aerosol profile. We need to know aerosol microscopic properties that define through me theory, aerosol single scattering albedo, aerosol asymmetry factor, which is dependency of the intensity as a function of the angle relative to which the light kind of hits this particle. We need to also, account for the fact that molecules scatter light too, Rayleigh scattering, which is wavelengths dependent. Also, we also need to know the surface albedo, although it's not as big of a contributor. And we also need to know where we're looking relative to the sun and more. So how do we untangle this information? So it's usually done through this quantity called air mass factor. in a very, very broad definition, it's a ratio of our slant column density or density along that, convoluted path relative to the vertical column density. And you can also compute this value if you know the information about your atmosphere. So if I have a radiative transfer model, and if I know the temperature, pressure, if I know the aerosols, where they are, how many particles are there, what kind of exact properties, I can model the intensity with and without the gas of interest, and I can use these fairly simple equations to calculate the air mass factor at some observation geometry and at the specific wavelengths. Okay, so to make life more interesting, obviously we don't just want one value, we want the whole profile dependency, and we call it box air mass factors, which is kind of like a name that is not probably the best. The best way to think about it is to think about it as a weighting function in a sense. It's a normalized weighting function. So this is a definition if you were to use a weighting function, just a weighting function, that intensity weighting function that is calculated by the radiative transfer models, normalized by the intensity and the vertical profile of this gas, the optical depths of the gas that you're interested in. So why I'm talking about this is the best, this weighting functions or the sensitivities are the best way to visualize and evaluate where your information is coming from. Remember, measurements themselves are quite simple. You just have a spectrometer, you have some kind of fiber, you have a telescope, you're pointing in different directions. Like there are simple ways you can do it. And then you have that information. So how do you go from this, like along some convoluted path that you don't know what it is to actual measurement that is meaningful, or, gas profiles? And this is where you need to understand the radiative transfer in the atmosphere. And this is where this box air mass factors or weighting functions come into play. So when we talk about atmosphere, we're kind of talking about two different cases, one linear case and non-linear case. Remember Beer's law, it's an exponential law. So you can see that under some conditions you will have non-linear behavior, and under others you'll have linear behavior. So aerosols, unfortunately, are non-linear, and the trace gases are linear. So you can split, in a sense, your retrieval in two different parts. You can say, if I know my aerosols, then I can easily derive my trace gases. So I'm not going to go through everything, but here's our sensitivity. So now you're looking at the sensitivity. So what do I mean by the sensitivity? What I mean is that if I take these curves here and multiply by the profile, trace gas profile, I'll be able to predict my measurement or my differential slant column density. And, from that, I can actually, provide the best information about the path and provide my vertical distribution. So this is for direct sun. As you can see, that it's totally flat. It means that it has absolutely no sensitivity to the profile, unless you get into Solezinus angles that are getting like large, so 80 degrees, or here's 85. Then you need to be a little bit careful because there is Earth's curvature, and then life is becoming more interesting, and you need to account for the stuff. But also the signal is becoming much slower, and then you have stray light that is coming into instruments. So people typically kind of try to stay away from long observations at really high Solezinus angles. So this is kind of like a 3D image of what you see on the left. So what does it mean from a point when you're scanning? So from a scanning point of view, now what you're looking at is where exactly I'm looking. So Usually, like if you're thinking about solar zenith angle, it's usually angle measured from the normal to the surface out. So the largest solar zenith angle will be when the sun is down, and the lowest when the sun is up. So if we have the condition when the sun is up, and when we're looking, 90 degrees to where the sun is, relative azimuth angle, and this is for 360 nanometers. I hope really appreciate the complexity of this problem. And if we have lower Ersal loading at this wavelengths, this is how the sensitivity will look like. So if I'm looking down at 85 degrees so it's 5 degrees elevation from the ground up, you can see that most of my information is really coming from this first 0.5 kilometers. And as I continue looking up, that information is being shifted up and up. And then eventually I really don't distinguish between profiles, just like I do with direct sound data. So this is 360 nanometers. So I'm going to flip to 477 and we'll go back and forth. And you probably can see there is a difference. And that's another thing that we're doing in the retrievals is we're playing with different wavelengths to be able to actually optimize our information that we're trying to squeeze through. So at 360 nanometers will be less scattering, and the information will be coming from closer where we are versus where where there are 470 nanometers. So you can see wavelengths, species, all this needs to be characterized and brought together to be able to actually extract that, very useful information that is hidden in the intensity measurements. So let me check. Okay, 233. So what I'm going to quickly talk about is the effect of aerosols on the. So I just said that aerosols represent like a modifier to what otherwise molecular scattering will be. And but what does this mean from the information point of view? One, of course, we have to retrieve the aerosols to be able to retrieve the trace gases. But two, do they modify it in a way that can be somehow beneficial to extract some information from some parts of the atmosphere versus the other? And again, I want to explain why I'm looking at these two particular wavelengths. So one of the things that we have in the atmosphere is oxygen. So oxygen is an incredibly important molecule for obviously life, but it's also an incredibly important molecule for DOAS, max DOAS community. The reason for that is that oxygen collision complex, which is just a collision complex between two oxygen atoms, actually has absorption within like at 360 nanometers and 477, very strong pronounced absorption. And the beauty of that is that we as a community think that oxygen is equally distributed in the atmosphere. So if you have a measurement, that measurement does not depend on the emissions, like it will be with nitrogen dioxide or anything else. And it's mainly if the stuff, are different and stuff, it's only because of the aerosols or clouds. So it's our magic molecules that allows us to actually derive the aerosol properties by looking at the absorption of the oxygen collision complex. So I'm looking here at two different aerosol optical depths. So what I mean is the integrated optical depths due to aerosols through the entire atmosphere. And this is a two profiles. So this is for 360 nanometers and 477. And, this is, what you'll call low versus high. The bottom line, what I'm trying to see is how well this, presence of aerosols can interfere with my measurements or maybe help my measurements, and what happens to my sensitivity to various profiles in the atmosphere. So I'm not going to go through all this. I told you this is an old presentation that I bored somebody for a long time, probably. This is just this again sensitivity. This is height on the left axis. I guess it disappeared somehow. And box MS factors on the bottom. Again, this is a sensitivity of the measurement to the profile. So what I will do, if I had that profile, I'll multiply the profile at each altitude by this value and then add them together, and that would be my measurement. So you can see that at 477 nanometers, like I am, the sensitivity is almost 20, 1 EMF at the bottom. So if I have a lot of emission at the bottom, like I'll have a very strong signal. And obviously, as it goes up, the sensitivity is getting down, so you actually can provide the profile at each altitude. So what happens if I have aerosols in the atmosphere? So this is low aerosols. Now I'm saying, okay, like there's a fog or something is happening and it's just like low overloading the atmosphere. And this is the difference. So what we're seeing here is that as there are more and more particles are in the atmosphere, the information is going to be squeezed in a sense to the surface. So this is a difference. This is the information that I'm losing in a sense. So you can see that the information from the upper layers are being removed from the measurements, and what is left is what is closer to the surface. So in a sense, it's actually not a bad thing if you're interested in near surface concentration. So like if you're in a environment, say like, airports where there are a lot of aerosols produced due to different processes, like you actually, like encourage this because, or you like this because all the information is really coming from the surface. So you can actually identify what's going on. So obviously, again, because of the Rayleigh, we have different sensitivities, and I'm not going to bore you through all these different cases, but the logic behind it is that you can switch, you can, consider different cases, and you can actually use different wavelengths to, maximize the amount of information that is coming from your intensity measurements, and as a result of this. So I'm going to go to further down and just kind of, that was a long presentation. So what I'm going to do is kind of talk about the actual mechanics of the retrievals. So what do we have? So in a sense, the whole measurement is really, you have differential slant column densities at multiple evaluation angles. You're looking, at the intensity, which is just a footprint. It's a remote sensing technique, just a footprint of what you actually want to do. And then you want to retrieve the entire, whoever left that footprint with the colors and shapes and absolutely everything else, like a vertical profile for trace gases or aerosols. So what are your inputs and how good your problem is? So the inputs are typically your measurements, differential slant column density measurements at several elevation angles for one scan. So you go boom, 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 boom. You take a measurement above, you take it as a reference, and you have this differential absorption. So it means the absorption along those different paths. So your real goal is to try to have a high resolution vertical profile from those limited number of measurements. And of course, if you think about it, it's a ill-posed problem and there might not be a unique solution. So how do we deal with that? I'm not going to go through optimal estimation details here, but the idea is that you are trying to simulate weighting functions, and it's an iterative process to figure out what the solution will be. However, what I do want to emphasize, this is obviously statistics, is Bayesian solution. So it relies on a priori knowledge of the species and its covariance matrix. to constrain the solution. So what does this mean? It means that you're propagating your a priori information into your solution. How realistic that is for aerosols, this is a huge, the variance of the a priori can have pretty large errors just because, it can go from, no aerosols to pretty high levels if you're in urban environments. And in addition, obviously your solution depends on the measurement area itself. So in a sense, this approach works if you have very good information about what's going on, but in most cases, you actually don't have that information at all. So, there are, as I said, there is linear and nonlinear problem. The linear problem is easier. Nonlinear, you have to simulate your K or your weighting function for every single case instead of just simulating the profiles. So there are different ways of retrieving that, but usually the MaxDOAS community goes in these two steps. First, they retrieve Ersal Ersal inversion, where they use O2 data, and that produces the profile. Single scattering albedo is typically taken from somewhere else. A symmetry factor typically taken from somewhere else because that information is too deeply hidden in the data that with these techniques, it's difficult to invert. And then after you have the aerosol profiles, then it's a linear problem, and then you can just retrieve the trace gas using a linear non-least square fitting that I just kind of discussed. So there are the actual implementation can vary, but the bottom line is that you need to have some kind of forward model simulation. So this is radiative transfer measurement. You have your inputs from your measurements, and you have your a priori information. So, you feed all this into your, non-linear least squares fit or linear, depending on the problem. And it's an iterative process, so it goes back and forth until it comes up with some acceptable difference between the measurement and the solution. And as a result, you get the And as a result, you get something that might not look what you want, but that's the best you get. So the beauty of this type of techniques is that you usually have a fairly good estimation of your error because it's a statistical approach. The bad part is that I think this actually limits the information that we can actually squeeze. So I think you can see that there is a lot of information, that there is a lot of simulations and all kinds of stuff here, but this is their technical part, I guess. Like I have a ton of presentations that have results with different approaches, and but this is pretty much what I kind of wanted to talk about today. So the idea is we start with photons and we end up with something like this beautiful dinosaur with every eye color and stripe color and everything, and we put an error bar on it too. Okay, if I didn't bore you enough, I'm open for questions.
Yeah, thank you very much. Thank you very much for that, Elena. Yeah, it's a little bit, at least for myself, to take in, but maybe others here on the call might have some questions for you. I'll maybe ask one simple thing. Can you relate this, and sort of because I have some insider knowledge, can you somewhat relate this to the measurements that you're doing with the equipment out of the tracking station, maybe?
Okay, so yeah, so we have an instrument at the tracking station. It's actually not DOAS technique instrument, but it's actually, let me stop sharing and I will open that site. What we have at the tracking station is actually a NASA AirNet instrument. And let me open, so let me share. So that instrument measures total AOD. And that technique, compared to what I just talked about, is the actually absolutely calibrated instrument. So it's not a differential like I talked about. It's not hyperspec. Well, it has multiple wavelengths, but it's a filter. Instrument has 9 filters covering the various wavelengths. Let me show. So this is AirNet. So it's a NASA sponsored ground-based validation network for Ersal optical depths validation around the globe. So so what I'm going to do, I'm just going to type Virginia Tech. So you can see that we are one of the sites. There are, I think, about 470 sites worldwide. And what I'm going to do is to show our measurements. So one thing that we had some technical issues earlier, but one thing that I'm always curious about being here is the impact of Redford ammunition plant on us. I don't know if you know, but we are literally 10 kilometers downwind from Redford ammunition plant, which actually burns about 40% of their ammunition in open fire pits. Okay, so they have some ways that they cannot put into hazardous waste incinerators because they can explode. So they literally like have areas where they just let stuff blow up and burn. So I always was curious, like how much of that actually we see here. And you know, the instrumentation has been traveling all the time, so we didn't really get that much opportunity to look at, you know, like what we actually have here. But one thing that I have noticed, so what you're looking at, this is the Ersal optical depths. Again, this is absorption, the total extinction. So it's absorption and scattering through the entire atmosphere. And you can see that in summer, we tend to have higher values, and in winter, we tend to have lower values. So the question is, the spikes, what are those spikes? So like, this is something that we're quite interested. We actually have 3 instruments on the roof right now running, doing all kinds of interesting measurements that are DOAS instruments, looking at the trace gases. And this is sort of a combination, like we see, you know, aerosols from those instruments and this instrument to really describe what's going on. So there are what 9 filters here, 1, 2, 3, 4, 5, 6, 7 filters. So it's from 340, 380 nanometers, 440, 500, 6 to 1020. And if I look at any specific day, so right now, so let's look at November. It was a little bit kind of clearer day. So like so for example, if I'm looking at these days, this is how our Aerosols look like, actually quite low AOD. And I have been kind of watching for the trace gas pollution, because I'm expecting there will be nitrogen oxides coming from the Redford plant. We have not seen it yet, but I'm looking to see if I can capture that increase in aerosols and see if we can actually also link it to the other gases that are in the atmosphere that can be the result of the Redford ammunition plant burning. But if I were to go to Beijing or something like that, these values are going to be significantly higher, just because there are all these other sources and stuff. So this is fairly good. You know, I would say that it's a very clean environment so far. And in general, it's still a mystery to me what we're seeing here. But I don't know if I answered your questions, but I think I kind of dumped on you a lot of information.
No, that's okay. I think going back to it was something that you said earlier, that it basically it's a different technique, which is a good starting point. That yeah, that instrument's a different technique than kind of what you talked about earlier. Thank you.
Mm-hmm. Yeah, and you know, like if you're students, so you can get on this website, and what I really like here, this is a network. So there are over about 500 470 or something instruments, and like if you want to look who is nearby, or if you are interested if there is an instrument where you're from, you always can find that instrument and get an idea how good their air quality is. So aerosols are actually dangerous for human health, especially as small particles like less than 2.5 micron, because of the they launch in our lungs, or they can actually even penetrate into our arteries and cause wide range of problems from cancer to heart attacks, strokes, and other things. So, seeing low levels is actually good. So in addition to this, we also have a ceilometer on our roof. We have full sky camera. It's not as easy to get to them right away. I should have probably opened to them. So in a sense, with the trace gases, total AOD, with the CMOL, which is it's a laser technique that sends the pulses just like a radar, just with a laser, and determines the backscatter from the aerosols in the atmosphere. And then, full sky camera gives us information about the cloud cover, how much interference do we have due to cloud cover. So we actually have a very nice package of the measurements right now to be able to characterize pretty much everything about this environment from radiative transfer point of view and pollution. Yeah.
Well, thank you very much. Any other questions from anybody there? Because maybe had a little bit of time to think here.
Are the students always quiet, or is it just a special occasion?
It's not usually this quiet, but I suspect it being, right before fall AGUs next week and being reading day tomorrow in the end of our semester, that's probably got a little bit of things to do with that.
So, Kevin, when you invite speakers, I guess I didn't ask for any guidance, what you wanted from the speakers. What do you usually kind of encourage the presenters to talk about?
It's whatever they would like to talk about, something that's interesting and neat that's related to space. That's the kind of rough guidance that I think I've given to this. So, right, so it doesn't necessarily have to be even novel research. Like we had earlier in the semester a review of the UPROSAT program or project, which is really pretty new, and they were just kind of going over some of the very big highlights of what's going on with that. It wasn't very technical detail. So yeah, it can be pretty, pretty high level. Let's say the only thing, and there was one I loved last year that actually just talked about space as far as kind of like regulations and kind of policy type thing with kind of space traffic and space awareness kind of thing, with the idea that there's a lot of satellites that are going up and how that affects not only optical astronomy but also like RF astronomy, right? So there was anything about orbits or any of that type of stuff. It was just more of about like the policy of that, and I thought that was a very interesting. Interesting talk. So yeah, that's I think the only requirement is it's something that's related to space. So.
Okay.
Yeah, if there's any other questions, feel free to jump in here. I'll give it maybe just a second for people to reach the mute button. All right. Otherwise, I'm not hearing anything. So thank you very much to Dr. Elena Lin, and hopefully I can give a round of applause sort of here. I'll give it into my big empty room that I have here. yeah, thanks so much for presenting today and closing out the fall semester for the seminar series. I was very, very thankful for you to step forward and presenting here. So very, very good.
So next time we'll have some shiny pictures from different campaigns. All right. Well, thank you, everybody, and good luck in your exams and happy holidays and whatever else is coming. So.
Yeah, that's right. Like as I said before, yeah, I'll be announcing some things coming up for the new or for the spring semester for the seminar series. But yeah, this is it for the semester. So thanks so much.
Bye, everybody.
Thanks, Dr. Lenz.
Thank you.